Hello, welcome to Linear Models, and we are going to take a minute to do this warm-up. Please pause the video and give these a try. First step is to try to get a common denominator of 60, so we're going to multiply each fraction, the top and bottom, by the factor required to get to 60. And then I'm just going to write the numerators because then what I would do is multiply every term by 60 to get rid of the denominator, and I'm left with 20x equals 30x minus 75 because we're multiplying each thing inside the bracket by 15. And then I'm subtracting 12 of everything in that third term, which is minus 36x and minus 24. Last step is to collect like terms and get all your x's onto one side. Please be mindful of your negatives when you are collecting like terms. And your final answer is minus 99 over 26. I never promise you pretty numbers. Practice for exponent laws here. Now you have a negative exponent, so be aware of how to deal with negative exponents. Simplify the top, do the power of a power on the denominator, and now we've got x to the power of 8 over x to the power of minus 8. And for the quotient law, we subtract the exponent, so this becomes 8 minus negative 8, or, like I used to say, when a negative is unhappy, to make it happy, flip it to the other side of the fraction and make it positive. And there's your final answer. We can use the area model for this. I'd rather do the over strategy. So instead of trying to do 18 times 53, let's do 20 times 53. Because remember, we're trying to get 18 groups of 53. Well, if we do 20 groups of 53, it means that we did 2 extra groups of 53, which is easy to subtract because it's 106. And of course, 20 groups of 53 is easy because it's just 2 groups of 53 plus a 0. So now we just take 1060 and subtract off 106. So 1060 minus 100 gives us 9060 to take away 6 more, and we get 984. And you can double check that one on a calculator if you want. So we're looking at linear models, and remember that a linear model represents any quantity that increase or decrease by a constant amount over equal intervals. So in your table of values, you would look at the rise versus the run, or the x changing as in relation to the y changing, and those first differences will always be equal. Your graph is a straight line. Your graph can be the equation of the line can be represented by y equals mx plus b, where m is the slope and b is the y-intercept. There is a constant rate of change. Your slope is never changing. These are all the ways that you can tell that you have a linear model. Which one of these models represents a linear relation? Remember that x is always your independent variable and y is always your dependent variable, and that time never stops for anything. So whenever you have something with time in the question, you know that that is always going to be your independent variable. So this is x and this is y. This is x and this is y. So you're looking for, okay, so as time goes up by a second, the height is going down 5 meters. As the time went up by a second, the height went down 15. The time went up by a second, and then it went down 25. This is not linear because the slope or the rate of change is not constant. For the second example, our hours are going up by 5, so the x is going up consistently. The y is going up by 40, also going up consistently. So we can tell that for every 5 hours, I make $40 or I make $8 per hour. This is a linear relationship. Just looking at these graphs, which model represents a linear relation? Well, which one of them is a straight line? Pretty obvious that this depreciation in value on the printer is going down at a steady rate, and it's going to be worth nothing in 5 years, and it started at $500, so it is losing $100 a year. Sorry, I misread the graph. It's losing $120 a year. Apologies. And because it is losing value, our slope is negative. The surface area of the cube, this, by the way, is quadratic. It could look exponential at this rate because we can't go into negative surface area or negative side length, but surface area of a cube is a squared function, so therefore it is a quadratic relationship, or just not linear. From an equation, which model represents linear? Well, the whole point of linear is that it has a degree of 1, meaning there are no exponents in the equation. Which one of these has no exponents? Well, that would be this one. So therefore, E is linear, and F has an x squared in it, which means it's quadratic, or just not linear. Last example, a cup of coffee is reheated in a microwave. The temperature C degrees Celsius of the coffee after T seconds can be modeled by the linear equation. So a 500 watt power setting, it's going up by a half a degree every second, and a 1,000 watt power setting saying that it is going up by 1 degree every second. How do I know that? Told me in the question that C was degrees in Celsius, so I am calculating the temperature of the coffee. T is time, which means that it's going to be changing per second over time. So in the 500 watt power setting, the 0.5 represents the increase in temperature per second. And then the 1 in the 1,000 watt power setting says that it is increasing 1 degree per second in the 1,000 watt microwave. This last asks you to graph both equations on Desmos, and then how are the numbers in the equation reflected in the graph. Here is a screenshot of the two equations graphed on Desmos, and you can see that the 20 represents the y-intercept, and it is the same for both lines, and how the going up at 1 degree per second line is blue, and the half degree per second is red. And this is telling us that the coffee started at room temperature, or 20 degrees. And as you can see, going up by 1 degree goes up faster than going up by half a degree. So that is it for our examples, and you can go ahead and work on your practice questions.